it's truly remarkable to realize the phenomenal strides we've made in the development of electronic technology over the past half-century. Starting with massive mainframe computers that sometimes occupied entire buildings, today we can create computers that fit in our pockets, yet possess capabilities that were once unimaginable for their predecessors. Indeed, there's a noticeable progress in electronic technology today compared to what was available 10 or even 5 years ago. To illustrate, try running a modern game on a computer that was considered powerful not too long ago. Overall, the evolution is happening swiftly and impressively. This is fantastic because it provides us with increasingly powerful tools for work or entertainment. However, it's not all smooth sailing, as the advancement of modern electronics is gradually encountering natural limits imposed by the physics underlying the technologies. One of these challenges, among many, is the high energy consumption of modern electronic technologies. While it may seem counterintuitive at first, devices like mobile phones and computers appear to consume relatively little energy. Nevertheless, today's electronic devices, including computers, smartphones, tablets, etc., already account for about 25% of our household electricity consumption. This figure is projected to rise to 45% by 2030. Additionally, a significant amount of energy is consumed by the information infrastructure, including internet services that operate colossal computing power. For instance, Google annually consumes 15.5 terawatt-hours of energy, equivalent to the entire energy consumption of a small country like Slovakia. It's estimated that processing just 50 Google search queries requires enough energy to boil a cup of water. According to forecasts, if current development trends persist, by 2035, global electronics and its associated information infrastructure will consume as much energy as the entire Earth currently generates. Thus, maintaining the status quo will require hundreds of new power stations in the very near future just to meet the voracious appetite of our gadgets. Fortunately, there are technologies that, with proper development, can significantly reduce the energy consumption of electronics by thousands of times. Moreover, these technologies have the potential to enable the creation of even more powerful, faster, and efficient electronic devices. One such promising avenue is Spintronics, which we'll delve into today. In essence, Spintronics is already widely used, and spintronic technologies are likely employed to some extent in the computer or mobile phone you're using to watch this video. However, this is likely just the dawn of spintronic technologies, and in the near future, they are expected to find much broader applications in technology. Currently, hundreds of scientists and thousands of engineers worldwide are putting in substantial efforts to make this happen as soon as possible. So, what is spintronics, and how does its concept differ from the traditional concept of electronics? In the classic concept of determining the state of a particular logic element, we observe whether an electrical current is flowing through it. If there is a current, we say that the logic cell is in the 1 state. If there is no current, we say that it has a 0 written to it. Any electric current is essentially the directed movement of charged particles, electrons in the case of computers. To make a computer work, we constantly have to drive trillions of electrons through its electrical circuits, consuming a significant amount of energy to set them in motion. Moreover, this current is typically passed through semiconductor materials, which, as the name suggests, do not have very good electrical conductivity, or, in other words, they have relatively high electrical resistance. This means that a significant portion of the conveyed energy is wasted. Furthermore, as the performance of an electronic device increases, the proportion of energy wasted also rises. To create a more efficient electronic brain, we need to pack more semiconductor logic elements into the same volume, so these elements have to be as small as possible. It turns out that the smaller the element, the greater the proportion of energy it consumes in vain. So here's the deal. The concept of spintronics suggests a shift in the approach, using the spins of electrons as the source of information about the state of logical elements, rather than the flow of electrons and their presence or absence. Speaking of what spin is, we have a separate video on that. What's crucial now is that an electron's spin determines its magnetic moment. In other words, thanks to its spin, each electron becomes a tiny magnet. In space, this magnet can be oriented in only two ways. Its axis can point either down or up. Theoretically, we can use the orientation of an electron's spin and its magnetic moment as a carrier of information. Let's say we assign the spin-up state a value of 0 and the spin-down state a value of 1. Consequently, to change the state of a logical cell, we don't need to accelerate or break the electron. We just need to flip it, turning 0 into 1 or 1 into 0. More precisely, in practice, it's usually done differently by comparing the spins of two electrons, or even more precisely, two groups of electrons. If their spins are oriented in the same direction, we say that the element is in state 1, and the opposite spin direction indicates that the system is in state 0. As you can see, the idea behind spintronics is quite straightforward. However, its implementation is more challenging. Firstly, controlling the electron spin is not easy. Since flipping an electron requires very little energy, it's quite challenging to make electrons flip only when needed and avoid flipping when it's unnecessary. On the other hand, distinguishing an electron with its spin pointing in one direction from an electron with its spin pointing in the opposite direction is quite tricky. Nevertheless, scientists have discovered a series of effects where the behavior of electrons depends on the direction of their spins and magnetic moments. Engineers have figured out how to apply these effects in practice. Perhaps historically, the first discovered effect, where electrons with different spin directions behave differently, is called magnetoresistance. It turns out that when an electric current flows through a magnetized material, the electrons with their spins aligned more strongly scatter, and consequently experience greater resistance if the magnetic moment of their electrons is directed opposite to the magnetization of the material. Conversely, electrons with a magnetic moment aligned parallel to the magnetization of the material move through it more easily with less resistance. However, this effect turned out to be not very significant. The difference in resistance was only a fraction of a percent, making the effect almost useless from a practical point of view. However, in 1988, a much stronger effect called giant magnetoresistance was discovered. This effect occurs in layered nanostructures consisting of ferromagnetic and ordinary non-magnetic metals. Interestingly, it was discovered almost simultaneously in 1988 by two groups of scientists, led by Albert Fert and Peter Grunberg. Grunberg's experiment studied a stack of thin layers of iron interleaved with chromium layers, while Fert's experiment involved another ferromagnetic material, cobalt, interleaved with copper layers. It turned out that the conductivity of such structures depends heavily on how the ferromagnetic layers are magnetized. If their magnetizations were parallel, the resistance of the sandwich was significantly lower than when they were anti-parallel. It's important that the metal layers are very thin, on the order of nanometers. A complete and accurate explanation of this phenomenon requires a deep dive into the theory of electrical conductivity, particularly the theory of electrical conductivity in transition metals, as well as quantum mechanics. Very briefly, it can be explained as follows. The boundary between the ferromagnetic and non-magnetic material can be thought of as a surface separating two media. An electron passing through the material can either pass through this surface or reflect from it. It turns out that electrons whose magnetic moment coincides with the magnetization of the sample have the highest probability of passing through the plate, and those whose magnetic moment is anti-parallel to the magnetization have the highest probability of reflecting. Accordingly, if the plates are magnetized the same way, for example upwards, electrons with an upward-directed magnetic moment will pass through the layer cake relatively easily. However, those with a downward-directed magnetic moment will struggle. Conversely, if one of the magnets has an upward-directed magnetization and the other has a downward-directed magnetization, the upper electrons will easily overcome the first boundary with the non-magnetic metal, but they will struggle to pass through the boundary between the metal and the second magnet. On the other hand, the lower electrons easily cross this second boundary, but are almost absent in the current flowing through the non-magnetic metal, as they reflect from the boundary between the metal and the first magnet. Therefore, in the end, the current will be small at the same voltage, corresponding to a higher observed resistance. The difference in resistance of the layer with different polarities of the magnets can reach tens of %, making the effect noticeable and measurable. In simpler terms, we apply a known voltage to our stack, measure the current, determine the resistance, and based on that, deduce the magnetization direction of our magnets relative to each other. More precisely, we will have maximum current when they are magnetized parallel to each other, minimum current when magnetized in opposite directions, and a whole spectrum of intermediate current values when the magnetization directions are at some angle to each other. The idea of how to use this effect is right on the surface. It can be used to develop extremely sensitive sensors for magnetic fields, specifically the direction of the magnetic field. Let's make one of the magnets, or rather one of the ferromagnetic substrates, of our sandwich massive, so its magnetization doesn't change. On the contrary, make the other one very, very thin, so that even a weak magnetic field significantly influences the vector of its magnetization. Now, magnetize our ferromagnetic layers in a perpendicular direction. Let's say the upper massive sample is magnetized to the left, and the lower lightweight one is magnetized forward. If we now bring our stack to a magnet also magnetized to the left, its magnetic field will slightly deflect the magnetization of the light magnet to the left, making the mutual orientation of the magnets closer to parallel. This leads to a decrease in the resistance of the stack, and we can detect this reduction by increasing the current through it at the same voltage. If the magnetization of the sample is directed to the right, the magnetization of the light magnet will also deflect to the right, making the orientation slightly closer to anti-parallel. This results in an increase in resistance and, consequently, a decrease in current. This construction is called a spin valve. Furt and Grunberg had just published their works when IBM engineer Stuart Parkin realized how significantly this could improve a widely used device like a computer hard drive. As you know, information on a hard drive is stored as a sequence of magnetic cells, each of which is magnetized by a recording head, essentially an electromagnet, either up or down. Between cells with opposite magnetization directions, there is magnetic flux, while between cells magnetized in the same direction, there is none. The disk's read head determines if there is magnetic flux between adjacent cells. If the read head detects flux, it indicates that a 1 is recorded. If not, it's considered that a 0 is recorded. To make hard drives as capacious as possible, we need to make magnetic cells as small as possible so that the area used to write 1 bit of data is minimal, maximizing the number of bits of information that can fit on the disk. However, the smaller the cell size, the weaker its magnetic field will be. Therefore, the read head must be more sensitive. Before the discovery of giant magnetoresistance, the maximum capacity of hard drives was in the hundreds of megabytes. However, read heads based on the giant magnetoresistance effect turned out to be so sensitive that they allowed increasing the disk capacity by thousands of times, to hundreds of gigabytes. This was the first and very significant victory of Spintronics. And today, each of us benefits from this victory. If your computer or laptop has a hard drive and it was manufactured in the 21st century, I can assure you that its read head operates based on the giant magnetoresistance effect, essentially representing a spin valve. But that was just the beginning of the story. A little later, a similar effect to giant magnetoresistance, but even more powerful, called the tunneling magnetoresistance effect, was discovered. The scheme is similar, the same layer structure, but instead of a metal layer, an insulator dielectric layer is used. As we know, an insulator does not conduct electricity, but very thin layers of dielectric, just a few nanometers thick, still allow electrons to pass through them due to the tunneling effect. Again, it turns out that the tunneling transition occurs significantly easier if the polarities of the magnets are directed in one direction, and much more difficult if in opposite directions. If in the case of giant magnetoresistance, the difference in resistances is tens of %, in the case of tunneling magnetoresistance, conductivity can change by orders of magnitude. Giant magnetoresistance was quickly harnessed for more efficient data reading from computer memory, while tunnel magnetoresistance could be utilized for creating the memory devices themselves. Indeed, in a scenario where magnets are magnetized in one direction, corresponding to minimal resistance and maximum current, it signifies a 1 stored in the memory cell. Conversely, when magnetizations are antiparallel, resistance is maximal, and current is minimal, indicating a 0. Reading the state of such memory cells is straightforward. By applying resistance to our sandwich and measuring the current passing through, we can determine the resistance. Due to the substantial tunnel magnetoresistance effect, only a minimal current is required to notice differences in conductivities. This technology, also known as magnetoresistive random access memory, MRAM, may not compete with hard drives due to its inability to provide the necessary data density, and the manufacturing cost per cell is comparatively high. However, the idea of replacing computer RAM with spin valve-based devices seemed very attractive. The most prevalent technology for manufacturing RAM today is dynamic random access memory, DRAM. Each DRAM cell storing 1 bit of information essentially functions as a tiny capacitor. A charged capacitor represents a 1, and a discharged one represents a 0. However, any charged capacitor tends to discharge over time, and the microscopic capacitors in DRAM lose their charge very quickly. To prevent all 1s in DRAM from turning into 0s, capacitors must be constantly recharged, leading to a constant and significant power consumption. Magnetoresistive memory overcomes this drawback. Once a sandwich is magnetized to represent 0 or 1, that state persists until it needs to be changed. Additionally, reading information from such memory takes less time, making it generally faster. This is why magnetoresistive memory, or MRAM, has long been discussed as a potential replacement for traditional DRAM. However, this transition has not happened yet, primarily because MRAM has one significant drawback related to the data writing process. To write something to a magnetoresistive cell, you need to magnetize the variable magnetic layer. Initially, this was done using electromagnets, similar to hard drives. However, this method proved highly inefficient in a microscopic scale, and today, a different technology is employed in MRAM microchips. Magnetization is achieved by passing a current through the cells. Let's assume our sandwich has a permanent magnet directed upwards, and the variable layer is magnetized downwards, representing a 0, as discussed earlier. Now, if we need to change its magnetization to switch from 0 to 1, we apply a current from right to left. Electrons from the permanent magnet, predominantly magnetized upwards, will flow into the variable magnet. When the number of upward electrons transferred becomes sufficiently large, their magnetic moment will dominate, and the magnet's polarity will switch to the upward direction, achieving the desired magnetization change. If we want to change the polarity back, we simply apply a current in the opposite direction, causing electrons magnetized in the same direction as our magnets to predominantly tunnel, while those with opposite magnetization accumulate in the variable magnet, eventually causing it to switch its magnetization. Since we're dealing with ferromagnetic materials, they will retain the acquired magnetization for a very long time. While this seems beneficial, the problem is that significant currents are required for such magnetization, as electrons need to tunnel through the dielectric. Consequently, this process is associated with considerable energy consumption. Therefore, MRAM excels in the read mode, but faces challenges in the write mode. Moreover, MRAM cells currently have a somewhat larger size compared to DRAM, leading to slightly lower data density. So, while MRAM cannot compete directly with DRAM, it is mainly used as a processor cache memory, storing frequently accessed information that doesn't require frequent rewriting. At the moment, MRAM competes not so much with DRAM, but rather with static random access memory. Although SRAM slightly outpaces MRAM in speed, MRAM does not require constant power, and it boasts higher data writing density. If you're interested, we can delve into more detail about existing memory types and the physical phenomena underlying them in future videos. Let us know in the comments. Regardless, the high energy costs associated with writing data in MRAM currently stand as a major obstacle preventing the widespread adoption of this technology. A vast number of scientists and engineers worldwide are actively seeking solutions to overcome this challenge. I won't delve into all the methodologies being developed today. Instead, I'll share insights into one approach, the creation of so-called spin currents, which allow us to saturate our material with electrons whose magnetic moment is precisely aligned in the desired direction. Imagine that, somehow, we manage to pass a spin-polarized current through the variable magnetic layer, a current where electrons predominantly possess a specific spin value. Similar to passing a current through the tunnel junction we discussed earlier, if the current exceeds a critical value, the cumulative magnetic moment of the conduction electrons in the conductor will reach a sufficient magnitude to magnetize the conductor, achieving the desired result. In this case, we no longer need to pass the current through a tunnel junction with high resistance. Instead, it can flow through a well-conductive ferromagnetic material, solving our primary problem. The only remaining challenge is to somehow create a spin-polarized current by separating electron flows with different spin and magnetic moment directions. Currently, several methods exist for generating spin-polarized currents. I won't list all these methods. Instead, I'll focus on the most prevalent one, the so-called spin Hall effect. The regular Hall effect involves the creation of a potential difference in a conductor through which an electric current flows when placed in a magnetic field. Here, we deal with basic school physics. The magnetic field acts on moving electrons with the Lorentz force, perpendicular to both the direction of motion and the magnetic field. Let's say the magnetic field is directed outward from the screen, i.e., towards the viewers. In this case, the Lorentz force will deflect electrons to the left, resulting in a higher electron concentration on the left side of the conductor compared to the right. This leads to the accumulation of negative potential on the left border and positive potential on the right. The spin Hall effect operates on a similar principle, but there's no external magnetic field. Instead, the effect is achieved differently. Consider the movement of electrons through a metallic conductor and their interaction with the atoms, specifically positively charged ions, in the crystalline lattice of the metal. Transitioning to a reference frame linked to the electrons, where the electrons themselves are stationary, while the ions move in the opposite direction and back, these moving ions generate an effective magnetic field in the electron's reference frame. It's crucial to note that in this reference frame, electrons are stationary, and the magnetic field acts on moving charged particles. Therefore, electrons won't perceive the impact of this effective field, as is the case with the Hall effect. However, they will feel this field due to their intrinsic magnetic moment, resulting from their spin. Depending on whether their spin is directed up or down, electrons will be deflected to the left or right in the effective magnetic field created by the moving ions. A sort of separation occurs in the electron flow, initially consisting of a mixture of electrons with magnetic moments pointing up and down. One wall of the conductor will have an increased concentration of electrons with an upward-pointing magnetic moment, while the other will have those with a downward-pointing magnetic moment. If we now connect conductors to each end of the material, creating a potential difference across them, we'll observe a current flowing through these conductors. Crucially, this current will predominantly consist of electrons with a specific spin direction. Essentially, it will be spin-polarized. While this effect is not very significant because magnetic interactions are relatively weak, there are various ways to enhance it. For instance, using a conductor made of massive atoms of heavy metals like tungsten, iridium, platinum, or gold. Currently, there are many technological intricacies to amplify this effect. Yet we are still far from the ideal in this regard. Consequently, scientists are exploring alternative methods to generate spin-polarized currents, such as using special materials known as multiferroics. It's another intriguing topic that we won't delve into now, as our discussion has already been quite extensive. And there's something else we need to discuss. The generation of pure spin currents opens up fundamentally new possibilities, offering the potential to create even more efficient technologies for memory storage. Enter the realm of what's known as Racetrack memory, a technology currently being developed by many leading companies, including IBM. By the way, one of the pioneers of this technology is Stuart Parkin, the creator of hard drives based on the GMR effect. According to Parkin, Racetrack memory could potentially replace both the RAM and cache memory in conventional computers, as well as flash drives and even traditional hard drives. The working principle of racetrack memory somewhat resembles that of film cassettes. The data carrier is an elongated object, in this case, a long and thin thread made of ferromagnetic material. The thread is divided into domain zones with varying magnetization, much like those in a magnetic cassette or a hard drive. Unlike a hard drive and similar to a cassette, the reading and writing heads remain stationary. However, unlike a cassette, the thread in racetrack memory does not move mechanically. Instead, by passing a pure spin current through the thread, we can induce movement in the domains themselves. The magnetic field of the thread causes the electron spin, passing through the domain to rotate. However, Newton's third law still applies, and as the magnetic field affecting the electron, it also causes a slight rotation in the magnetization of individual crystals in the magnetic domains, specifically in the walls of these domains, where the magnetic moments of individual magnetic grains gradually rotate, separating one domain from another. By passing a certain amount of spin-polarized electrons through our conductor, we can achieve the migration of domains along the thread, although the thread itself and even the atoms composing the thread remain stationary. Since the focus is on domain walls, racetrack memory is also known as domain wall memory. Such memory can have a capacity exceeding that of hard drives and be cost competitive with them. Still, since it lacks mechanically moving parts, it should operate much faster and be more reliable. In terms of speed, this memory can even outperform DRAM, SRAM, and even MRAM while consuming much less energy during operation and not requiring constant power, unlike DRAM and SRAM. In theory, racetrack memory could replace the entire hierarchy of memory devices used in modern computers. However, even though the technology was proposed back in 2007, as of the recording of this video 15 years later, creating a functional racetrack memory based on this technology has yet to be achieved. There are numerous reasons for this. For example, no matter how weak the current required to move domain walls is, in ultra-thin nanometer-sized threads, the flow of such currents would result in significant heat generation that could almost instantly burn through the delicate threads. Another issue is the speed of domain wall movement. Theoretically, it can reach thousands of meters per second, but in practice, speeds achieved as for today are only in the tens of meters per second, which is clearly insufficient. Scientists from various countries are actively working on solving the problems associated with racetrack memory. They are exploring various approaches, with some suggesting the use of magnetic skyrmions, spin vortices capable of stably existing in a magnetic environment and moving within it at relatively low energy costs, similar to how toroidal vortices move in a gas, such as smoke rings. Simultaneously, experiments are underway with multiferroics, layered nanostructures, and piezoelectric materials. Each of these topics could potentially be the subject of a separate, albeit not very brief, video. And racetrack memory is just the tip of the iceberg when it comes to what Spintronics has to offer. Spin transistors have already been developed, although these devices are currently not miniature enough to replace conventional transistors and suffer from various issues, such as sensitivity to temperature increases. However, this is just the beginning. If the topic of Spintronics seems interesting to you, let us know in the comments, and perhaps we'll delve into specific aspects of this technological development in more detail in our future videos.